That's the sound of a black hole feeding on a star. Not a simulation, not movie sound effects. That's real data, converted into something your ears can actually process. But wait, black holes are silent, right? Space is a vacuum. Sound can't travel through nothing. So how did scientists at MIT actually record a black hole eating? By the end of this video, you'll understand exactly how astronomers turn light into sound, what those eerie tones actually represent, and why the discovery is completely changing how we study the most destructive forces in the universe. We're going to break down what happens when a black hole feeds, how scientists use light echoes like cosmic echolocation, and what that haunting sound is really telling us. Let's get into it. Before we decode that sound, you need to understand what's actually happening when a black hole decides to eat. There are tens of millions of black holes scattered across our Milky Way galaxy alone. Most of the time, they're invisible, dark, silent, just sitting there in the cosmic void. But every once in a while, a black hole gets hungry, and when that happens, things get violent. Picture this. A black hole and a regular star, locked in a gravitational dance. The star orbits the black hole, minding its own business, but the black hole's gravity is relentless. It starts pulling gas and dust off the star's surface, slowly at first, then faster. The stolen material doesn't fall straight in, it spirals, it swirls, it forms what scientists call an accretion disk. A glowing whirlpool of superheated matter spinning around the black hole at nearly the speed of light. And here's where it gets spicy. Friction within that disk heats the gas to millions of degrees, hot enough to emit X-rays, hot enough to outshine entire galaxies. That's when astronomers can finally see a black hole. Not the hole itself, but the chaos surrounding it. And in 2022, a team at MIT figured out how to listen to that chaos. They found a way to map a black hole's feeding frenzy using something called light echoes. Stay with me, this is where it gets really cool. Alright, let's talk about the anatomy of a feeding black hole, because it's way more complex than just a disk of hot gas. You've got the accretion disk we just talked about. Think of it like a cosmic pancake, flat and spinning, made of stolen star material. But above that disk, there's something else. A region of superheated plasma called the corona. This thing is insanely hot. We're talking billions of degrees, not millions, billions. The corona is so energetic that it blasts out high-energy X-rays in all directions. Some of those X-rays shoot straight toward Earth, but others, they bounce off the accretion disk below. And that's the key. When those X-rays hit the disk and bounce back, they create what scientists call a light echo. Think about it like echolocation. Bats navigate dark caves by making sounds and listening for the echo. The time it takes for the echo to return tells the bat how far away the walls are. Same principle here, except instead of sound, astronomers use X-rays. Instead of a cave, they're mapping the space around a black hole. Here's how it works. The corona fires off a burst of X-rays. Some reach our telescopes immediately. Others bounce off the disk first, arriving a fraction of a second later. By measuring that tiny delay, that time lag between the direct X-rays and the echoes, scientists can calculate the distance between the corona and the disk. They can literally map the shape of a black hole's feeding zone without ever seeing it directly. Professor Erin Kara at MIT has been perfecting this technique for years, and in 2022 her team made a fascinating discovery. Until recently, only a handful of black holes in our galaxy were known to produce clear X-ray light echoes. Scientists were not sure whether this was a rare trick of nature or something far more common. Then a team at MIT built the Reverberation Machine, an automated algorithm designed to search massive datasets for the telltale delays that reveal black hole echoes. The data came from NASA's NICER instrument, short for Neutron Star Interior Composition Explorer. It is an X-ray observatory mounted on the outside of the International Space Station. As the station circles Earth about every 90 minutes, NICER's changing viewpoint lets it observe different X-ray sources across the sky, from neutron stars to feeding black holes. When the MIT team ran NICER's data through their system, they began finding echoes in far more systems than expected. These were not the supermassive black holes in the centers of galaxies, but smaller ones, 5 to 15 times the mass of our sun. Every one of them lived in a binary system, orbiting a normal star, one visible, one invisible, until the moment it began to feed. By comparing how the echoes changed across different systems, the team traced patterns in how black holes shift between what astronomers call hard and soft states. In the hard state, the corona is energetic and jets can form. As the system transitions, the X-ray signal changes, possibly as the corona expands or rearranges itself. And that leads to the final question. If all of this is written in X-ray light, how do you turn those echoes into something you can actually hear? Space is silent. We all know that. Sound needs molecules to travel through air. Air, water, something. The vacuum of space has nothing. So technically you can't hear a black hole. But scientists have a workaround. Professor Erin Kara teamed up with Kyle Keene from MIT's Department of Materials Science and Engineering and Ian Condry, a professor of anthropology and music, to convert the X-ray data into audible sound waves. The technique is called sonification. You take data that exists outside human perception and translate it into something our senses can process. They mapped X-ray frequency to pitch. Lower frequency X-rays became lower pitched sounds. Higher frequency X-rays became higher pitched sounds. The timing of the echoes became rhythm. The intensity of the X-rays became volume. What you're hearing is the signature of a black hole's corona, irradiating its accretion disk. X-rays bouncing and reverberating in the most extreme environment in the known universe. We can basically hear the general relativity. Think about that. General relativity. Einstein's theory of how gravity warps space and time. You can hear its effects in that sound. But this isn't just about making cool sounds. Sonification helps scientists detect patterns that might be invisible in raw data. The human ear is incredibly good at picking up subtle changes in rhythm and tone. By listening to black hole data, researchers can sometimes identify features that might have been missed just looking at graphs. So, what did all these echoes actually teach us about black holes? Turns out, quite a lot. In 2019, Kara's team made a separate discovery using the same technique on a black hole called Maxi J1820+070. That's about 10,000 light years away in the constellation Ophiuchus. By tracking the light echoes over several weeks, they noticed the time delays getting shorter and shorter. The echoes were coming back faster. Something in the system was getting smaller. That something was the corona. It was contracting, shrinking from roughly 100 miles across to just 10 miles across. To put that in perspective, that's like a region the size of Manhattan collapsing down to something smaller than Central Park, made of billion-degree plasma around a black hole. Even more interesting, the analysis showed that the corona appeared to extend vertically above the disk, like a pillar of superheated plasma shooting upward. That shape suggests the corona might be connected to the powerful jets that black holes sometimes blast out at nearly the speed of light. Professor Erin Kara said these black hole binaries appear to be mini supermassive black holes. She said by understanding the outbursts in these small nearby systems, we can understand how similar outbursts in supermassive black holes affect the galaxies in which they reside. But those processes happen over billions of years, impossible to observe in real time. Stellar mass black holes, like the ones making these echoes, go through similar cycles in just months. They're like laboratory-scale models of cosmic evolution. Here's the thing. We've been studying black holes for decades. We've imaged their shadows, we've detected their gravitational waves, but actually mapping what happens right at the edge, the feeding zone, that's been almost impossible. These black holes are thousands of light years away. Even the best telescopes can't resolve the tiny region near the event horizon. It's like trying to see a quarter of the moon from Times Square. Light echoes give us a workaround. We don't need to see the structure directly, we can infer it from timing. This technique is opening doors. Scientists are now actively hunting for more echoing systems. The more they find, the better they can understand the universal patterns of black hole feeding. The NICER telescope recently needed repairs. Astronaut Nick Cage actually did a spacewalk in January 2025 to patch up damaged thermal shields on the instrument. So here's what we learned. 1. Black holes aren't always invisible. When they feed, they produce X-ray bursts that bounce and echo off the surrounding gas. 2. MIT's Reverberation Machine found 8 new echoing black holes in our galaxy, proving this phenomenon is far more common than we thought. 3. By measuring the time delay between X-ray bursts and their echoes, scientists can map the structure around black holes without ever seeing it directly. 4. Sonification turns that data into sound, letting us literally hear the chaos near a black hole's event horizon. If you like this video, please do subscribe and turn on notifications. We're just getting started.